Well, a warm welcome, everybody. Thank you for joining. Get yourself ready with a notebook, grab a pencil or a pen, whatever you choose to write with, it's fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have the final sixth problem from the 2025, that's this year's AP Calculus AB exam. And this is the final of the batch. It's also the final of the non-calculator section. So you might have looked at this one last, might be the last problem that you did on the exam. That would be interesting. When you're all fatigued. Well, here you have another shot. If you didn't get to it in time, or if you just weren't thinking clearly, missed something, whatever the case may be, go ahead and give yourself about 12 to 15 minutes. This one's a bit longer. There are 4 parts here. Work the problem out yourself. Could be redemption, could be a victory lap. And then when you're ready, you can unpause the video, come back and join, see how we did it here. Alright, without further ado, let's get started. We're going to start by considering the curve, not the function, because this curve has y's in multiple places, defined by the equation of y cubed minus y squared minus y plus 1/4 x squared equals 0. So the first thing they want us to do is they just want us to show, it's pretty easy, show that dy dx equals this expression. And it's kind of nice that they give you, sort of a destination, place where you should end up to confirm that you did it correctly. It's also part A though, so it's pretty easy. I think it's clear that implicit differentiation is required because of the y's in different places. Also, they didn't mention function, they just mentioned the curve. That's kind of an indicator sometimes. And we don't have anything crazy. There's no product rule, chain rule, there's no sine, cosine, or e to a power. It's just polynomial terms. So it's pretty easy to take a derivative. Let's go ahead and do that. Take a derivative of both sides here. It's going to become 3y squared dy dx minus 2y dy dx. Don't forget the dy dx term every time you take a derivative of y stuff. Let's fix this a little bit. Yeah, that looks a little bit better. Minus just dy dx, because even though the derivative would be like a 1, we need to use the chain rule on y. Y has its own derivative called dy dx. And then plus 1/4 times 2 is just a half x equals 0. Now if we want to get dy dx by itself, we're going to move the 1/2 x so that we have only dy dx containing terms on the right side. And we can factor the dy dx out, leaving us with 3y squared from the first guy. You see that? Just basically stole this from it. Minus 2y, again, stealing the dy dx, minus a 1 equals negative 1/2 x. Okay. And then I guess we're just going to divide. Yeah, just going to divide this term off. Now the negative 1/2 x, I'm sort of looking at the destination here, and you see that the 2 is on bottom. That's coming from the 1/2. The negative stayed up with the x. So that's kind of how they're choosing to write it. If you divide both sides, dy dx equals negative x stays on top. The 2 goes on bottom to join the thing that's being divided there. I mean, that's kind of just some basic algebra simplification. But hey, not everyone has those skills, so I might as well point them out. The AP exam is, after all, just a kind of long skills challenge. If you have skills, you'll pass it. If you understand calculus, you're more likely to be able to demonstrate your skills. If you don't understand calculus, you're relying on basic, rote memorization and hoping to the Lord that there's not, a really nasty function that makes you think about mathematics. So just understand the math and then develop your skills and you'll be in great shape. All right, part B. There's a point P on the curve G that is near 2 comma negative 1 as x coordinate 1.6. It wants us to use the line tangent to the curve at 2 comma negative 1. So maybe 2 comma negative 1 is on there. Maybe I'm misunderstanding this. There is a point P, on the curve G, near 2 comma negative 1 with x coordinate 1.6. That makes it seem weird. Okay, let's just plug this in so that I'm not guessing. Negative 1 cubed minus negative 1 squared minus negative 1 plus 1/4, and then 2 squared is just 4. So we get negative 1 minus 1 plus 1 plus 1. Yeah, that does equal 0. Okay, so aside from how weird that wording is, it seems very strange to me. The point 2 negative 1 is actually, or the point P, it says on the curve G. That's the part that's throwing me. And then later it says with x coordinate 1.6. So it's making it seem like P has a coordinate of 1.6, which I think is true. It's just that P is not on the curve. And what confirms that says use the line tangent at this point. It can't be tangent if it's not on the curve. So I guess we're going to use that tangent line there. Pretty simple to use the tangent line. We just have to find the dy dx. Let's write the equation of tangent line. You guys know the drill with that. We're going to have y minus y value equals m times x minus x value. And fortunately, we already have the x and y value. That's pretty nice. This is going to be y minus negative 1. I'll put it in properly for now. Equals whatever the dy dx is going to be times x minus 2. So let's find out what dy dx is at the point 2 negative 1. We can just say m, I guess. M equals negative 2 over 2 times 3 multiplied by negative 1 squared minus 2 multiplied by negative 1 and then minus 1. Let's move that. Being a messy Marvin here. Not everything's going to move, but let's see. Minus negative 1, get in there. Get your butt in there. Alright. So we have, well, these just cancel. So that's going to be negative 1 over 3 plus 2 minus 1. And just do all this stuff carefully, guys. The last thing you want to miss is like some points because you didn't do like basic arithmetic right, or you didn't change the negative when you squared it. Maybe you didn't change it to a positive. You kept it negative, and so your answer's off now. Lots of things can happen. Here's our slope. We're going to use that right here. And so the equation of tangent line at that point is given by this. Now we need to plug in x equals 1.6 because we're trying to find the approximate coordinates based on the tangent line since it's near our curve. This just means that y is going to equal negative 1/4 times 1.6 minus 2 and then minus 1. So negative 1/4 of negative 0.4, that's pretty easy. That's going to be 0.1, like positive 0.1 minus 1, negative 0.9. So we would say that the y value is approximately negative 0.9. You can write it wherever, you can write it there if you want to. That's what tangent lines let us do. They let us approximate values that are close to a curve. They don't give us the actual value, but they get us pretty close. All right, let's move on to part C. For x greater than 0 and y greater than 0, there's a point S. They're going to describe it. It's on the curve G, okay? So we know that the x and y fit in this equation, at which the line tangent to that curve is vertical. Find the y coordinate of point S. So that's huge that it's vertical. That's a really huge clue. If the line tangent to the curve is vertical, that means that dy dx is approaching like 1 over 0 in some kind of way. Maybe from the left, maybe from the right. The point is that the derivative, the slope, is approaching plus or minus infinity. And when would that happen? Well, that would happen if this fraction, 3y squared, this fraction had a 0 in the denominator, or I should say the denominator goes to 0. It approaches 0. As that happens, that means that this denominator term, 3y squared minus 2y minus 1, must be going to 0. And this looks like a fun quadratic to factor. It's going to be pretty simple. I would guess 3y plus 1 and y minus 1. So we would have y equals 1 and y equals negative 1/3. Now, why does it say there is a point? That's because if you look at the initial restrictions here, x and y have to be positive. So we're not even talking about this situation. We're talking about y being positive. Okay? Do we need the coordinates? We just need the y coordinate. That was actually really incredibly easy. I'm surprised. That's the y coordinate. Y equals 1. Doesn't even ask for the x coordinate. Alright, let's move on to part D. And we'll be done with this AP Calculus exam. Oh my goodness. Well, the free response part. You guys had to sit through the multiple choice. I have not seen the multiple choice. I don't think I'll see the multiple choice anytime soon, but I don't care. Alright, part D. Particle moves along the curve H. Alright, we got a new curve defined by this equation. Of course, got a new curve. At the instant when the particle is at the point P, dx dt equals 3. Find dy dt at that instant. What? I'm being silly. Dx dt and dy dt, that introduces a whole new variable, t. But this is just a, should I say, a differentiating variable. So let's write that here. When differentiating, let's make this a little smaller too. With respect to any variable, it just means that any other terms which are also variables will require implicit differentiation. Alright, so what is this implicit differentiation idea? Kind of the same thing that we did with dy and dx. Like whenever there was y stuff, we just wrote dy dx. Very similar to how a related rates problem would look, right? If we have a height that's changing over time and a radius that's changing over time, maybe something else that's changing over time, you can write those as like dh dt or dr dt. They're both changing over time. So let's use the curve, take a derivative of it. They give us some conditions. They tell us that particle is at this point, so they give us the x and the y. That's kind of nice. It's going to help us. They give us this dx dt, which I guess is going to help us at some point if we take a derivative of the x stuff, which it looks like we will. And then we have dy dt. That's what we're looking for. Find dy dt at that instant, which means all of these conditions are applying. So really you just have to take a derivative. And let's do that. We're going to have the product rule. So we're going to have 2y, 2 dx dt times y plus 2x dy dt, see how that works? Both with respect to time, plus the derivative of ln is usually just 1 over y, but now it's going to be 1 over y dy dt. And that equals 0. Okay? So just use the conditions they gave you. You have that the dx dt at that point is 3. You have that the y value at that instant is 1. The x value is 4. We don't know dy dt. That's what we're solving for, but it's going to reveal itself very quickly here. Plus 1 over, well, just 1 times dy dt equals 0. So altogether we have 6 plus 8 dy dt plus 1 dy dt. I'm purposely doing this very carefully and slowly so that we have negative 6 equals 9 dy dt. And that means that dy dt is simply negative 2/3. All right, so what is significance, like visually? I don't even know what that graph looks like off the top of my head, to be honest. It's not your responsibility to know what the graph looks like. You just need to be able to use the derivative correctly, apply the initial conditions that they gave you. I'm surprised we didn't have to solve a differential equation. We just had to use some implicit methods. And then very tricky wording. I don't like the wording on part B. In fact, I'll probably hit up the College Board and be like, yo, can you guys work on how you type some of these problems? Because these kids are working hard enough to do the math. Part C did also require some interpretation, but I think it was written really well, actually. Part C is a great question. It's asking where the tangent line is vertical, and they give you some sneaky little conditions there. So that was actually kind of cool. All in all, I would say this was a good problem. What they were trying to get out of you anyways is great. I just think the way they worded Part B was kind of terrible. In any event, that'll do it. That was the full 6 questions from this year's AP Calculus exam. Hope you learned something. If you're going to take BC next year, don't you dare forget not a drop of this elixir of life that we call calculus. Don't lose a drop. Savor it. There's more to come next year. And remember that the BC exam, it really is, I want to say 70% exactly the same as the AP exam. Some of the situations are exactly the same, like 65-ish, 70% of them, but there are some cases where maybe a free response question has the same equation, same curve, but different types of calc techniques are being required between the AB and BC exam. That does happen. For example, they might have had you do some parametric stuff and find the length of the path traveled over a few seconds or something, which is not an AB topic. Anyways, I just have so much energy after doing these tests that I'm rambling a little bit. I think that's enough blab out of me. And I'll see you guys soon in the wood.